So the second talk is by Avery on SpEQ, which basically uses equality saturation for translation of sparse code.
Thanks. My name's Avery, and I'm excited to be presenting SpEQ. This is a joint work, actually, between University of Toronto and some folks at Microsoft Research. And the first thing I want to do is just show you right off the bat like an example of the goal of what we're trying to do here. So on the left-hand side, this is a snippet taken from the NASA Parallel Benchmark Suite, which for compiler people, you know, this is a very famous benchmark. And it's doing a matrix vector multiplication. And the matrix is stored in CSR. And I felt kind of silly like throwing up a slide about CSR at this workshop, so I'm going to assume everybody knows what compressed sparse row is, but if you don't, let me know. I can dredge up a slide about that. But anyway, so it's operating on a sparse matrix. And I'm coming at this from the perspective of a general purpose compiler person. And if you give this to a general purpose compiler, it will not be able to do anything for you. So wouldn't it be nice if instead you can automatically translate this code into like a library or a DSL that's already very good at executing this code for you. And so I have an example there. This is using cuSPARSE to offload to GPU. You can imagine a similar thing with MKL, and actually you don't have to imagine because it will do it for you. And we also support OMP as well. And an important thing to note on this slide is that if you want to do this translation correctly, which is a big emphasis of the tool, then you also have to make sure that the input, in other words, the sparse matrix in this case, is in the form that you actually expect. You have to verify some kind of precondition. And in this example, because the matrix is stored using CSR, we have to make sure that it actually does represent a sparse matrix at runtime, because it easily could not, depending on the input data. So I'll have more examples later in the presentation to explain all of that. But before I move forward, I also just want to clarify a bit of the motivation, because I think for practitioners, probably in the sparse domain, a lot of the questions come up for me is, okay, why not just do this by hand, or use one of the many existing tools out there? And it's definitely true. Like you can imagine, especially for somebody who knows sparse codes, they look at this, they immediately know what's going on. Okay, let's rewrite it to like the latest DSL. And there's two main issues I see with that. So the first issue is very tedious. So a lot of legacy codes that you're going to find this pattern in are they're old and they're big, and so you have to search through the whole thing, find these cases, make sure it's actually in a form you expect. And you can imagine that you do that, maybe you make a mistake. So it's also error prone. But you could do the whole process, and now it's in the newest, fanciest DSL. But there's a DSL born every day, and so there's all of these proliferation. And then what happens when the new accelerator comes out that your DSL doesn't support that accelerator yet, or it's not maintained anymore? You have to do the whole process over again. So what we're aiming to be is like the layer in between. These great tools that are out there that can generate super fast sparse codes for you, or maybe handwritten implementations, and some existing code you already have that you just want to automatically get into that form. Okay. So this is the general pipeline. We operate on LLVM IR. And I will go step by step through this pipeline just to explain the whole process using a running example. And we can take a look actually and compare what is possible just with this SPMV example that I showed in the previous slide. So on some of the benchmarks we tested on, there was 4 of the benchmarks that actually had some kind of SPMV happening in there. And we support, for this version of the paper, OpenMP, MKL, and cuSPARSE. And so this should not be surprising, right? It would be really weird if you weren't getting really high speedups. So I'm not showing this to say, okay, we get amazing speedup and that should be impressive. More, I just want to give some indication of what's possible when you step away from relying on the general purpose compiler to do something and find the global maximum of performance. Okay, so let's start with the first stage of the pipeline, which is where we try to figure out what storage formats are actually being used in the input code. So there's the running example again on the left. And on the right, I'm showing kind of like a cartoon. It's not totally accurate, right? There's more detail hidden underneath. But this is a graph to represent the relationship between definitions in the program of variables and the usages between them. So for example, we have some J induction variable, and it has a range, in this case, from 0 to m. And this arrow is to indicate that it's used by this other range below, from row j to row j plus 1, and so on. So that's how to read this graph. And as I mentioned, everything here is in the LLVM IR, so I'm just showing the source code here, so you don't have to parse a bunch of LLVM IR. And so we can generate this graph very straightforwardly from the IR. And then we also have, a library, a database of a bunch of different storage formats that are used in these types of codes. And this is not something we made up. This is very, very, very well explored already in previous work. And for each of these formats, you can generate kind of like a template version of this graph that has the same structure. So I'm going to need some kind of V2 that has some sort of range, and some arrays in here that have very particular constraints as well. And so you can try to create a correspondence between what you actually have in your input code and what you expect to see in codes that use a particular storage format. So this very first step is just a way to give you a very rough guess about what kind of storage formats might be in there. And there's more details in the paper about how the matching works and everything, but I'll just leave it here for the talk. But of course, this is a guess. So it's not at all guaranteed that it will be correct. There's two main things that could go wrong. So the first thing is you could have made a correct guess in the sense of all of the correct structure is there, all of the variables that you need are in the program, but at runtime, it's actually doing something different. So this is an example on the left to show some data that doesn't actually represent a sparse matrix. So to call a code like this with this input data in SPMV is wrong. It's not actually doing SPMV. It's maybe doing something else, or maybe it's a bug. But anyway, we can't call it SPMV. And the other issue is that there might be some format or some other structure that SpEQ just didn't match or didn't understand. And given all the different types of formats, that's not so hard to imagine. And so we want to have a way to make sure that we guard against these two cases. And the way that we do that is through an equivalence check. So how it works is we have this input code, and it's operating on some sparse format, so in this case, CSR. And we have a guess that this is CSR, but we don't know for sure. So what we can do, based off our knowledge of CSR, is we can create a version of the input program that looks like it's operating densely. So we can try to factor out, we can invert the compression process, try to get a version of the program that looks like it should be dense, and that's represented by this dense matrix below. And these two versions of the program, if we made the correct guess and we detected all of the storage formats, they should be provably the same program. And if we miss something, then they will not be the same program. So the next question is, okay, how do we actually prove that these are equivalent? That's not a super straightforward thing to do. And here, these next two slides, I just want to give like a broad intuition of how it works. I have some slides after with like actual detail, but I'll go quickly over those because it's a bit complicated for a shorter talk like this. But how it works is we could have two possible cases between these code versions. Like the original input code version is on the left, and the code version that we created is on the right. And one possibility is that they're both processing the same elements at the same time. And in that case, we can prove equivalence for each step just by checking that these states are equivalent. And visually, it's fairly easy to see, okay, yeah, these should be equivalent. But the sticking point is when you have this kind of thing happen, which is the dense version of the code is processing all of the elements, including 0 elements, not just non-zeros. But the input code is sparse, and so it's allowed to skip 0 elements. And we have to be able to relate these skipped states back to the dense version of the program. So that in transition system terminology, that's called stuttering. And I have an example of the transition system snippet on this slide, where the dense code is taking one extra step. In other words, it's processing this 0 times P4, while the sparse system is idling in this same state. And this red dash is to indicate that these two states are related. In other words, they're equivalent, because if I add 0 to this, I get the same thing as before. Okay, so we can prove these are equivalent. And for anybody who is interested in the details, this is how the joint system itself is actually created. So we smush all of the variables together from each program. We conjunct the initial states of the program, and then we have a relation where this is the dense program. It will always take a step. But the sparse program has two choices. One choice is that if there's no zeros to process, it will have to take a step. Or if there are remaining zeros to process, it will idle. This represents the idling transition. And we wrap this up into a proof rule that I'm just showing for the fancy formulas. But the main part of this formula rule is SR3, where we're able to prove that these two programs are equal in all reachable states of the transition system. And this is an example instantiation of like what these relations actually kind of look like, just to give you an idea. So like when both systems are processing the same elements, we have a certain predicates that are true. And when the dense system is processing a 0, then we have to make sure that we're asserting that there is a 0 stored in the dense version of the matrix. And this M represents a way to measure the distance of how many zeros there are still left over to process. And this is a way to guarantee that the dense system will always catch up back to the sparse one. Okay. So for more detail, yeah, you can take a look at the paper. I don't want to, bog everyone down in the details here. And the final step is we want to try to recognize the dense version that we created as having some sort of knowable semantics. So in this case, we'd want to recognize it as a GEMV. And we do this through equality saturation. And Max already did a really great job of explaining EGRAPHS. So I won't re-explain everything here, but basically we have some written reference implementations in like C or Fortran, whatever you want, as long as it gets into LLVM IR. and we generate a rewrite rule from each reference implementation. So if you give me a reference for GemV, then I'll create a rule that says every time I see this in the eGraph, you can just rewrite it to this kind of, you can think of like uninterpreted function label. And then we also take the format-free code that we generated, we create a term out of it and put it in the eGraph. And now, because of the rewrite rule we had before, we can e-match on these two symbols and assert that, OK, now they're in the same equivalence class. In other words, we've proven that our input code has this mapping to what we call a GemV. And the final step for translation is basically a lookup table. Like if we know the input code is GemV and we know that it's using CSR, GemV plus CSR, SPMV. And we can, for cuSPARSE, we know, OK, this cuSPARSE call relates to GemV and CSR, this OMP call, so on. Sorry, MKL call. So we have an evaluation over 10 different benchmarks and different formats. And the spec itself is actually not specific to sparse code. Like it's designed to handle types of sparse code, but we also can handle like reduction, histogram. Like I said, anything you give us in the reference implementation, spec can search for it using the quality saturation. And we also compare against some other tools that do a similar sort of thing, but we're the only ones who actually check the preconditions to make sure that it's correct. Okay. We're also not too slow in terms of latency. So even though the whole thing is implemented in like Python, we're usually fairly close to the O3 pipeline at LLVM, which is multi-threaded C++. So there's not a huge overhead here. So the main idea of this tool is you should be able to give us a reference implementation of some code that you're interested in finding, and we can go through, as we compile your code, we can go through and look for instances of that and let you decide, OK, I want to offload to this or this or this. And the artifacts are available online. There's instructions for how to add your own kernels that you want to look for and add your own backends. So please, feel free to download it, give it a try, and let me know, what bugs there are and everything. But yeah, that's everything I wanted to talk about. So thank you very much for your time. Yeah.
Time for one question.
Thanks for the talk. So do I understand correctly that you're executing those precondition checks during runtime for every input matrix? And does it then even apply for a matrix vector multiply, where if you have a memory bandwidth bound operation and you have to scan actually the entire matrix to detect there are no duplicates in column indices, does it make sense to apply during runtime?
That's a very good question. It depends on the storage format, and it depends on the context of the code. For example, if you have an SPMV inside of a conjugate gradient code, the runtime check can be hoisted out of the conjugate gradient loop and easily amortized. You also don't have, the preconditions can be simplified greatly. Like you don't have to scan the whole matrix most of the time. But that also depends on format. But yeah, I can also discuss more with you after.
Thank you.
Please click this.